Hi, Bill here. This is the search.cpp source module in my simple chess engine. Okay, so this is search, so this is where it all happens. So we called our globals, we've got a few variables declared. So think is called from whenever the engine's told to look for a move. So it sets up a few variables. Now this jump's interesting. That's a way for the engine to jump out of search when it's starting to run out of time for that move. So this is part of the jump process for quitting the search. Okay, so if the search ends, then we're going to take back the moves that were in the tree at the point of the tree we're in, and then quit this function. Okay, so if we're using a fixed time, what it's going to do is if we made a capture or the and so forth, we're going to reduce the time allowed by half. That's not essential, that's just a little thing to change the amount of time it uses some moves. The kings in check will also change the time taken for that move. Okay, then we've got start and stops used for working how much time it's taken for the move. Okay, so we just update the position, and we're going to print out the current search principal variation. Okay, so the max depth is just the arbitrary depth we're going to search to, so we start searching. So we do what's called deepening iteration. So we search for a depth of 1, go back to start, search for a depth of 2, then we go back to start, search for 3, and so on. Okay, so we're just assigning something to the current. So current max just tells us what depth we're at. Okay, so again, we're checking the time and seeing if those conditions are met. We're going to stop searching. Now we call the big search function, which is really the heart and bones of everything. It passes to the search function minus 10,000, which is the worst possible score. It means you're in checkmate, and the best possible score, which means you've got basically you've got a checkmate position, but you're on the other side. So we know the true score will be somewhere in the middle of that. Okay, so we just get our root, start and dest, so that's going to be the move of the day. So we just print out some information here, and now we look up the if the positions in the hash table, the moves in the hash table, we're going to display the PV, which is the principal variation. Okay, so we're just going to, this breaks in case if we find a force mate, or we're going to get mated by force, we're going to stop searching. Okay, so what we do now is it's all in the search. So this is the search function. So if the position's repeating, that's what that basically does. We return a value of 0, which means the game is drawn, so we don't search anymore if we're repeating. If the depth is less than 1, so the depth is how much depth less to search. So say we were searching for a depth of 6 pi, and we were at a current depth of the maximum depth is 6, the pi is 3, that means we've got 3 more depth left. So if we're down to 0 or less, we don't do any more searching, we do our capture search. The capture search is important to stop it doing all sorts of blunders due to the horizon effect. Okay, so we increase our nodes by 1. The node is every position that looks at is called a node. Every 4,096 nodes we do a checkup. Now it's a fairly slow routine, that's why we only do it once every 4,000 positions. That just sees if we've got enough time left. If not, we're going to jump out of search. Okay, now if for some reason we go to some ridiculous depth, we quit the search as well. So if pi exceeds the maximum pi minus 2, we're going to just return the score for that position. Okay, so what we do now is have a best move and a best score and a check. So we want to see if we're in check, because that changes things. So okay, we generate the moves, if the position was found in the hash table, we set our hash move. Now, once we've generated the moves, we can go through them all one at a time. The moves are stored between start move and one less than start move, the first move, apply +1. So we sort the move, we choose the move with the highest move score. Then we make the move. If the move happen to be illegal, so if not make move, we just skip over that move, we continue. So we make the move. We keep a track of the number of legal moves, so we know, we can tell if we're stalemated or not. Okay, now, if the king's in check, we're not going to reduce the depth, so we're extending by 1. That's how an extension works. So we want to look at checks more deeply than other moves, so we extend by 1. If the move score has a values, or if pi is very low, or we happen to be in check, we do a normal depth search. Otherwise we do what's called reduction. Reduction's great, helps us stop looking at rubbishy moves, so moves that don't do anything. We search less than usual. The difficulty there is some of those quiet moves are actually quite good. Okay, then we do a recursive search, call to search again. So the value we get is x, so that's the score of the position ultimately. So we say minus, and we switch alpha and beta, make them minus as well. We pass the depth. So that's how we do the recursion. We take back the move. So what we did is basically we go through the moves, make the move, do a search, then take back the move. Okay, so if we get a good score, we're going to update the best move and the best score. Now this is where we do our big cutoff. So if x is greater than alpha, which is good, if x is greater than beta, then basically the position is too good, so we know that can't be the move. So we store. So if a move calls a cutoff, we're going to store it in the histories, we're going to change the history, and we're going to add it to the hash table. So we get the same position or the same move. If we get the same position, that's going to be sort of first when we're looking at moves. And if that move's played again, but in a different position, the history will mean it'll be higher in the move list. Okay, so if we don't get a cutoff, we raise alpha. So alpha starts low, beta starts high, and they gradually move together. So beta starts getting lower and alpha starts getting higher. Okay, so now what we're saying is, if we couldn't make a move, so C, remember C, that was the count of legal moves. Is at 0, we're either checkmating, so if we're attacking the king's under attack, it's checkmate, so we just got mated. Otherwise, it's stalemate, it's a draw. Notice, so checkmate score is minus 10,000. You add ply to it because it's better to checkmate in the shallower ply. Okay, so otherwise the engine will see a mate in 2 and a mate in 3. It will play the mate in 3. And then when it gets the mate, it's got a mate in 1 or a mate in 4, it might pick the mate in 4. So adding the ply stops it doing that, which I learnt the hard way. Okay, so what this is saying, if 50 is greater than or equal to 100, so 50 moves by both sides adds to 100, so if it hits 50, we return 0. The position can be scored as 0, and we're going to put the best move in the hash table, and we return alpha. So that loop, that just keeps going until you run out of time or it hits the maximum depth search, and it will return a more accurate score because the alpha and beta get closer and closer together. So capture search. So this is what we do when the depth gets the pi gets deep. So if we don't do that, we'll get all sorts of funny blunders. So it just sees if captures get anywhere. So first of all, we evaluate the position. You see we get a beta cutoff. Otherwise, we change alpha. Now, if the score is the difference between the score is greater than the queen, doesn't matter what we're going to take. We're not going to be able to make up the gap, so we don't bother looking at that. Okay, so set a few variables. We generate the captures, which is very like generating the moves. We zip around through the moves, we sort, so we look at the moves in their move order value. Okay, so what it's saying here is if the piece you're looking at is less than the different alpha, so in other words, if the gap is too big, we just skip over that capture. It's a bit like if we need to win at least a knight to catch up to alpha, and we're only taking a pawn, it's not even worth looking at. Okay, then we get the score from the recapture search, which is yet another search, and if the score is better than the best, we update our best score. Okay, so we get our best score, and now we're going to same sort of thing with x. X is greater than alpha. If the beta cutoff, we do this what we did before. Otherwise, we return the value of x. Okay, so and then we return alpha. So recapture search is a bit like capture search, but it's simpler because we're just taking on the same square. So it's a bit, in some ways, it's more complicated because we have this funny business where you work out the attackers and defenders of a piece, and then the basic idea if the value of the piece plus the piece defending it is less than what you're taking with, and it's guarded, it's not worth it. So if a queen's attacking a pawn guarded by a pawn, the queen's worth more than the pawn and a pawn. So even if you can get both pawns, it's just not worth it. So that's what that's about. Okay, so again, that's all part of the same algorithm, and then we count up all the pieces we took that both sides captured and recaptured on the same square. Okay, and then we take back the recapture. Okay, so repetition. So repetition searches to see if we're repeating the position. So it searches from the current position -4. We only search back the last 50 by that should be probably 50 times 2. Oh no, 50 is the count of moves since the last pawn move of capture. We're not going to, as soon as somebody's made a pawn move of capture, we're not going to bother seeing if the position's repeated or not, because we know it can't be. Okay, we go backwards by 2, so we're only searching for one colour. Okay, so if the hash equals the current key, in other words, it's the same position. If those two match the same position, there might be about a trillion chance. It won't be, but for all practical purposes, it'll be the same position. Okay, so that's what we do. So if we found a match in the position with the history of positions, we know we've repeated the position. Sort. So this is just finding the move with the best score in the move list. So we zip around through the loop of moves, and we search for the best score, and we so forth. Okay, so check up. So that just sees if we've run out of time. So the current time, that's what get MS is meets these conditions. Then we do this long jump. So we quit the search routine, set hash move. So what this does is, if the position happens to be in the hash table, we look for the legal moves, and one of them happens to match the hash move. We're going to give that the hash score. That'll mean it'll get sorted first. It'll be looked at first. Okay, display PV. Okay, so what this does is it loops through the moves until we can't find the resulting position in the lookup table, in the hash table. So what we do is we fetch the move out of the hash table, and that would be the next move in the principal variation, and then we just take back the moves. So it's much easier to do with a hash table than using things like what Crafty does. Okay, so that's it for the search module. Okay, so thank you for watching.